the angular momentum.
Hello, friends. Mr. Stone here. And today we're going to talk about angular momentum and angular kinetic energy. Now, you already had a taste of angular kinetic energy with the inclined plane rolling objects gizmo a couple weeks ago. And angular momentum, you've actually had a lot of experience with over the course of your life without being told about it. For example, when is it hardest to fall on a bicycle? Well, if you have a bicycle that's stopped and you try to put your feet up on the pedals, what are you going to do? You're going to fall over. But if you're moving, you're not going to fall off the side of the bike. Why? Momentum, when we're talking about translational motion, is how hard it is to get something to move some other way when it's already moving. For example, a semi-truck is hard to speed up, it's hard to slow down, it's hard to turn. And the faster it's going, the harder it is to achieve any of those accelerations. Remember, any change in motion is an acceleration. Well, if something's spinning, shouldn't it have a momentum to that too? If it's spinning one way, it doesn't want to spin any other way. So if your bicycle wheels are turning like this, and falling over would mean rotating like that, then they're going to resist that change. It is your spin momentum of the wheels that keeps the rest of you from spinning off to the side and hitting your head on the concrete. You've probably noticed this before with fidget spinners. Not that you're willing to admit that you played with fidget spinners, but you did. It's okay. We all did. It was 2016, 17. It was a great time. Once it's going, it resists any change into how it's going. In fact, I can let go of it with my thumb, and it resists falling off of my finger. Why? Because this spinning action stabilizes it, just like the spinning momentum of a bicycle's wheels keeps it from rotating off to the side. So you can balance this really, really well. You also get this with people balancing the spinning basketball on their finger. It'd be a lot harder to do that if it was not spinning, but because it's spinning, you get some stabilization from that. Speaking of sports balls, you also get this with a football. Why do you throw a football with a spiral? So that as it spins sideways, it doesn't spin end over end and tumble. You keep the pointed part spinning at a right angle to it, and therefore the pointed part of the football is kept forward. Because it's spinning that way, it doesn't spin any other way. It doesn't tumble, putting the broad side of the ball forward and experiencing a lot more air resistance. And it doesn't turn left or right. It goes nice and straight when you throw it that way. So spin momentum is an important thing, and you've encountered it before, whether you realized it or not. Remember that feeling when you have a fidget spinner really, really going, and then you turn it, that feeling of resistance, like you feel it kind of push back on you? That was due to angular momentum. We'll talk about that more in a moment.
For example, if you take a bicycle and the wheels are turning forward, look at what my thumb just did. If the wheels are turning forward, the momentum of the spinning wheels is directed to the left. If I hold this rope and release this wheel, what's it going to do? It'll, of course, flop this way, which means, look at my thumb, it would fall this way, which would give it momentum toward me, or at least the spin momentum would be directed toward me. But here's something interesting. If I gave it a lot of momentum in another direction, remember, momentum is the property you have when you're going and you resist any change in how you're going. So if I give it some momentum, it's going to resist turning in any other way. This is actually how bicycles work in the first place. Why don't you just fall over? Well, because you've got the wheels going. Alright, so now it's spinning this way really fast, and it's got a momentum this way. And of course, because this is a hoop, it's going to have a really big angular momentum. So you'd think it would want to flop over, but it doesn't. It stays upright because it is stabilized by the fact that it already has angular momentum.
If you're wondering why it appears to kind of wobble toward me, that wobble is called precession. Remember a moment ago I told you that you can use the right hand rule to find that if it did flop over from that tension and the unbalanced weight, it would have a momentum toward me. Instead, its momentum is directed out toward the side. Well, what do you get? Well, that torque is still there. It is still constantly trying to change its momentum in a direction toward me while being directed out to the side. So what happens? Well, that to the side momentum begins to chase me around and around. This precession also happens to larger objects. For example, this is why the Earth wobbles like a top does, causing the constellations' positions in the sky to change over many thousands of years. Or it does explain the wobble of a top as well. Linear momentum is mass times velocity. So it depends on two things. Your regular inertia, how hard you would be to move from, say, rest, just how your regular inclination against acceleration, but also it goes up with how fast you're going. So that you'll be harder and harder and harder to accelerate anyway as you were going faster and faster and faster. Each force would give you an even more subtle change than, say, if you were at rest. For angular momentum, all you have to do is translate everything. Get it? That's a bit of a pun. Translational motion versus rotational, right? The angular equivalent of inertia would be moment of inertia, I. The angular equivalent of linear speed or velocity would be your angular velocity. So instead of P for linear momentum, you get L for angular momentum. As usual, there is a one-step translation between the two that involves using the radius of the turn. Angular momentum can be found by multiplying your linear momentum times the radius of the turn. So that you can translate these two into each other. Also, starting here gives you a fun proof. Check it out. If this is the case, and this is also the case, so we should be able to put in mv for p. So L is mover, MVR, mass velocity radius of the turn. You end up using this one quite a bit. Well, V is also omega times radius. So let's plug that in. See if we get something interesting there. We would get multiply that R through. And you would get mr squared omega. Well, mr squared seems awfully familiar. I believe I remember that. Mr squared is moment of inertia for point mass. So if mr squared is moment of inertia, then we just proved that the first thing was true. Nice, right? The ones that you're going to have to use the most are these versions of it. So at the very least, get these into your notes, maybe this one too. If they're on your formula sheet, then I guess they're on your formula sheet, but you're going to need these and you're going to need to use them a lot. So write them out. Just get it into your head, drill it in the old-fashioned way. But all the other stuff about momentum still applies. For example, momentum of a system is conserved. Well, how do you find the momentum of a system? Let's say you're sitting still and someone passes you a basketball. Well, what's the momentums in that system before you catch it? Well, you would have your mass and velocity that you started out with. Perhaps you're running toward the ball, or perhaps you're sitting still. There would also be the mass of the ball and its velocity. If you put those two together, then we would have the total mass of the system, the total momentum of the system before. Same thing works for angular. You would have, let's say that you were sitting on a rolly chair and I pass you a basketball and you catch it at an angle. Well, then we would need to know your moment of inertia and your angular velocity at first. And then we would have that for the basketball as well. And if you caught it just right, you might start spinning in your rolly chair, which would mean we would have a non-zero total momentum of the system beforehand. All right, so that's old hat. But remember that we have conservation of momentum. Momentum is a conserved quantity, which means that the total amount of it in the universe, because the universe is a system, in any system, the total amount of momentum must remain unchanged. Anytime there's a collision, well, the collision doesn't change the total. So what you put in, you must get out. The total momentum before a collision is equal to the total momentum after the collision. That is true, be it linear or angular. Say you've got a block just sitting there, and it gets shot with a bullet. Well, obviously the bullet's going to have a lot of momentum, and the block just sitting there would have zero, but you add that together and you know the total momentum of the system beforehand. It is equal to the total momentum of the system afterwards. Now, in this case, they would stick together, so there would only be one final momentum. If they bounced and it was an elastic collision, then you would have multiple momentums afterward. But let's say you take a bullet and shoot it into a pendulum bob so that the pendulum bob begins to move in a circle. That would be interesting to do as well. You would have the total before equal to the total momentum after. But as you can see, the setup is still the same. Everything that you learned about collisions before is still going to be applicable now. One of the principles about conservation of momentum that you're probably still familiar with is Newton's third law of motion. If I want to put some momentum into you, apply a force to give you some momentum, then you push back on me, giving me a negative momentum equal in amount. In other words, for every push, there's a push in the opposite direction, just as hard. Well, that also applies, as you're seeing in the video, with spin momentum. The wheel is spinning, and I torque it. To torque it is a force to make it spin differently, but because it had momentum, it resists that change in its spin, and therefore it pushes back on me to make me spin the opposite direction. Let's try an example or two. A 200 kilogram satellite occupies a circular orbit of Earth at a distance of 12 times 10 to the 6 meters from the center of Earth. What is the angular momentum of the satellite? We're given a few variables here. The mass of the satellite is 200 kilos. The mass of the Earth is 5.972 times 10 to the 24th kilos. And the radial distance for the turn that the satellite is making. So the satellite is removed this much from the center of the Earth. So it's making a turn that big, 12 times 10 to the 6 meters. so 12 megameters. We want to know the angular momentum of the satellite. Well, that's either this, 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 or I guess we could do that. But notice, we don't have any of that stuff. All we've got is the mass of the satellite and the radius of its orbit. That would be enough to find the moment of inertia of the satellite, treating the satellite as a point mass, of course, but then we wouldn't have the velocity. Why then is the mass of the Earth given? Well, that circular orbit mentioned right here, that should have been a big neon sign flashing, screeching with sirens in your brain. Circular orbit, that means exactly centripetal force. When you've got a circular orbit, that means that the centripetal force pulling the satellite to turn is the force of gravity. Centripetal force is mv squared over r. Gravitational force is g, mass of the primary, mass of the satellite doing all the falling, divided by the radius squared. Bringing back warm, fuzzy memories from a semester ago. I like this unit being at the end. It provides some nice review. As Galileo taught us 400 years ago, the mass of a thing doing all the falling is never important. And we've got another common term in that R. And there we've found the velocity of the satellite. The velocity of the satellite is the square root of gm over r. Starting to feel familiar? Should. Let's go ahead and find that, and then it'll be pretty easy to do the rest of it. The velocity of the satellite would be the square root of the gravitational constant. It's been a while since we used that. I think I've got it memorized, but let's check. Hey, computer, what is the value of the gravitational constant in metric?
This might answer your question. The Newtonian constant of gravitation is approximately 6.67408 times 10 to the negative 11th cubic meters per kilogram second squared.
Thank you.
You're welcome.
All right. And the mass of the Earth is 5.972 times 10 to the 24th kilograms. Divide that by the radius of the orbit. And it's 12 times 10 to the 6 meters. Josh, trusty dusty calculator. Square root of, remember, put the entire numerator in some parentheses. Put the entire denominator in some parentheses. 6.67 times 10 to the power of negative 11. Close your first set. Actually, you know what? I'm going to leave that open. Times 5.972 times 10 to the 24th power. Now I'll close it. Divide by 12 times 10 to the 6th power. Close, close. And we have a quite respectable velocity of almost 6,000 kilometers per second. So 5,700 meters per second. With that, we now have the mass of the satellite for its angular momentum, the radius, and the velocity. So now we just use L equals mover. The mass is 200 kilograms, the velocity 5761.5 meters per second, and the radius 12 times 10 to the 6 meters. And it has 1.38 times 10 to the 13. Notice that 13 is not negative or anything. Kilogram meters squared per second. At this point, I want to take a quick note that kilogram meters squared per second. Well, let's go back to change in momentum. Remember that the units for regular momentum are kilogram meters per second, right? Because it's kilograms times meters per second. But kilograms times meters per second squared is force. Force is the change in momentum over time. Thus, it's the derivative of momentum over time for my calculus fans, or the second derivative over time of the location of something's center of mass. Good stuff. But getting back to good old-fashioned algebra, we can move that t to the other side. Force applied for a certain amount of time is called your change in momentum, or impulse, which for mysterious reasons is given J as its symbol. Torque then must be the change in angular momentum over time. Remember, torque is force times lever arm. Lever arm is a distance, so it'd be kilogram meters per second squared, force, times meters, making that meters squared. So the units kind of check out with what we were doing. If we move the t to the other side to find moment of impulse, not impulse anymore, but moment of impulse, then our moment of impulse would be kilogram meters squared per second squared times seconds. That gets rid of one of the seconds on the bottom. So a change in momentum, or angular momentum itself, should be measured in kilogram meters squared per second. Might be a good idea to pause that and go back a bit and watch it in half speed to make sure that you followed. But we have now introduced a new quantity, moment of impulse, the amount of change in angular momentum. Well, if impulse exists in linear stuff, it's got to exist for angular too. And it fits in when you're trying to think about what these units are. All right, getting back to my satellite, the 200 kilo satellite around the Earth. If it was to produce a burst of propulsion at the location shown here, so off to this side of the Earth, and it fires its boosters, what would the new orbit be? Well, it would be going faster, so the pull toward the center would be, it would change, right? You're going faster, and you'd be able to go out a little bit farther from the same gravitational attraction, and then that would weaken the attraction. So as gravity tries to like pull you back, it wouldn't be able to do so as suddenly. So you'd go out a little bit further, and then it would slow you down and then bring you back around to the same point. You would end up with an orbit that's no longer circular, it would be elliptical. If you have a speed change while orbiting, you get a nice ellipse. This is one of the things that astronomers like to look for when we are looking at the orbits of bodies going around stuff. the more elliptical it is, the more disturbed over time its orbit has been. For example, a nice respectable planet like Earth has been in the same spot, in the same orbit, at more or less the entirety of its existence. Why? Because it's big, it's massive, it's hard to move. But consider rinky-dink things like asteroids and comets. Comets are just big snowballs with dirt in them flung from the outer solar system. In the outer solar system, they are where they've kind of always been, far from the sun, where it's cold, hence why they're made of ice. But if they draw too close to another object, especially Neptune, they might get flung toward the inner solar system. A speed change, because obviously if you go downhill when you're pulled towards something, it's a gravity source, you speed up. That speed boost sends them shooting toward the sun, and they end up with these highly elliptical orbits. Some of them are so elliptical that they appear to be almost like cigar-shaped. An elliptical orbit is the orbit of an object that has been messed with. Look at Pluto's orbit compared to ours. Ours is nearly circular. Pluto's is much more similar to this red elliptical shape. Why? Because it got thrown around by Neptune like a comet. The second part of this, where would it have the greatest angular momentum? Well, the angular momentum would be conserved. It'd be the same everywhere. Like right here, when it's this close to the Earth, there's your radius here. L equals mvr. So your radius is small and your velocity goes up. Remember Kepler's laws. Johannes Kepler, taught us that when a planet is closest to the sun, it's moving faster in its orbit. The law of equal areas and equal times. But when it is farther away, it goes slower. Why? Well, it's got this angular momentum going around, and its radius has gone way up, so its velocity must go way down in order to compensate. Oh, you see this all the time and you don't even think about it.
This is used by figure skaters to control their angular velocity as they spin. Check it out. I've got these masses and I hold them out here versus tucking them in here. What does that do? That changes my moment of inertia. When is it higher? Out here or near my chest? Think back to the wheels with the ball bearings in them. The mass being farther away gives me a greater radius, and therefore, I've got a higher moment of inertia out here than in here. So let me give myself some angular velocity. And now I've got angular momentum. I put the weights out and I slow down. I bring them in and I start to speed up. If I put my feet out too, then I end up losing a lot of speed until I tuck them back in. So I'm using my moment of inertia to control my angular velocity because the angular momentum must be kept the same.
You also see this with space. Consider the strange case of a neutron star. A neutron star is the rotten corpse of a supergiant star. A supergiant star being one that's like 30 times the mass of the sun. Well, obviously that's going to be a big star. And they puff up when they die. As they're about to die, they balloon up to be red supergiants. And red supergiants can have diameters comparable to the orbit of Saturn around the sun in size. Let me run that by you again. Saturn's really far from the sun, right? And it makes this big orbit around it. You could have a star that fills up the same space.
Bruh.
Like it's huge. The sun takes about 1 month to go around its own poles one time. The Earth takes a day to go around its poles one time. Supergiant star, let's say for sake of comparison, let's say it's like the sun. It takes a month or a couple months to go around on itself once, to have one day. couple months. But then it collapses. A supergiant star collapses. It goes from being the size of Saturn's orbit to not just the size of, I don't know, Earth's orbit around the sun, or even the size of the sun, smaller than that. It goes from being the size of Saturn's orbit to being the size of the island of Manhattan.
Bruh.
It's a big drop in size, right? Like it gets really compacted. How does it do that? By taking all of the empty space in its atoms and forcing it together. Basically, the entire thing is as dense as the nucleus of an atom. But it's going around itself, right? And that radius goes way down. So what happens to your rate of spin? It becomes insane. Blink once. In the time it took you to do that, a neutron star would have had about 10 days. That is, it would have spun around on itself 10 times. This is what is called a millisecond pulsar, a neutron star that has a rotational period measured not in months or weeks or days or even seconds, but in milliseconds of rotational period. Powerful stuff right here. Here's another example problem. This one has a lot of quantities that you don't need, but let's read it. A cylinder rotates with constant angular acceleration about a fixed axis. The cylinder's moment of inertia about the axis is 4 kilograms times meters squared. At time 0, the cylinder is at rest. At this point, let's write out some of these quantities that are getting thrown at us. The moment of inertia is 4 kilogram meters squared. The initial velocity is rest. At time 2 seconds, its angular velocity is 1 radian per second. What is the angular momentum, so that's our unknown, of the cylinder at 2 seconds? Well, what do we need in order to find angular momentum? Just moment of inertia and angular velocity at that time. So at 2 seconds, it was going 1 radian per second and had a moment of inertia of 4 kilogram meters squared. 4 times 1 is 4, so we're going to get kilogram meters squared per second as our angular momentum. Is that easy? Of course, with all of this stuff, you could have found something more interesting. For example, you could have found the angular acceleration from the change in velocity over time, about half a radian per second, and then multiplied that by the moment of inertia to find the torque. Half times 4 would be 2 Newton meters of torque. So on and so forth. Sometimes you gotta make the question that makes printing all of this seem worthwhile. Kinetic energy is also a thing we need to worry about. I suppose there's also potential energy that matters, but potential energy would be in some other form. The potential to spin isn't necessarily a quantity that we need to worry about. It's just potential energy, and we've already covered potential energy, be it a spring or due to gravity or even due to electricity. But kinetic energy, when we're talking about linear stuff, K linear, or you could do translational if you want, but K linear is 1/2 mass velocity squared. So our angular would be 1/2 moment of inertia angular velocity squared. Easy peasy. None of this stuff should be terribly shocking for you. And in fact, we already kind of did some of this with the gizmo from a couple weeks ago, the rotational kinetic energy versus translational kinetic energy in that gizmo. And you had the chart where you could see both as it went down the ramp. Everything still applies to this. You know how to use energy. You guys loved energetics. It rescued you from kinematics, so you'll be indebted to it forever. You couldn't appreciate it more if you tried. Well, let's try an example problem to prove that it's just as easy as it used to be. So this one is really similar to our gizmo from a couple of weeks ago. You've got a ramp, and we have a sphere that's going to roll down it. A sphere of mass 2 kilograms, radius 1/2 meters, and in rotational inertia I is released from rest at the top of an inclined plane. So at the top of this 5-meter tall ramp, it is originally at rest, which means that it has no kinetic energy of any kind when it's at rest. The only type of energy it has up there is potential energy due to gravity. It begins to roll without slipping. Roll without slipping, or pure roll, means that it doesn't slide any. The only way that that center of mass is moving forward down the ramp is by rolling and acting kind of like a tire. Why? Because there's enough friction to allow that to happen. If you think about it, friction, as you try to roll like this way, is going to oppose. So the force of friction will be applied to the edge of it. Here's the radius. That's perpendicular to a lever arm going through the middle around this point. The force is the torque to get it to start rotating. No force, no force of friction would mean no torque. It doesn't rotate at all. So there is friction, there is a torque, it does have a reason to rotate, so it does. It picks up rotational kinetic energy as it goes down, because as it moves down, it experiences friction. So at the bottom, how fast is it going is what we want to know. Well, how fast is it going will be depending on how much of its energy that it had here went to making it go fast versus making it turn. So we have kinetic angular energy and kinetic linear. What we have here is equal to what we have here because energy is conserved. Nice and easy, just like it used to be. Mass gravity height before is equal to 1/2 mv squared and also 1/2 moment of inertia omega squared. When we write it like this, we've got a whole bunch of stuff that we're not given. So kind of like we did with the satellite, let's put it into some other terms that'll be something where we can find this in terms of these. Mass gravity height is 1/2 mv squared. I can put I in terms of mass and radius, so I will. The moment of inertia of a solid sphere, given right here, is 2/5 mr squared. And angular velocity can be put in terms of velocity and radius. It would be v over r squared. Move through with your like terms, combine stuff where you can. 1/2 mv squared. 1/2 times 2/5 would be 2/10 mr squared. V squared over r squared. You're beginning to see the light at the end of the tunnel at this point. Mass is everywhere, get rid of it. Radius is on the top and the bottom here, so get rid of that too. And it looks to me like we can do some more combining of like terms. 1/2 V, 2/10 V. 1/2 is 5/10. 5/10 plus 2/10 is 7/10. 7/10 V squared equals GH. Thus V shall be the square root of 10 GH over 7. Oh, well, what is that? Clear G times H would be 9.8 times 5 times 10/7. All right, so 70. Square root of 70, 8.3666. Since this one has two, I guess we could say this is 2.0 and say we're allowed to have 2 sig figs. So 8.4 meters per second. Square root of 70 meters per second is how fast it's going at the bottom of the ramp. Now the second part gives you a basis for comparison. If the surface had no friction and the sphere just slid down to the bottom, what would the sphere's velocity be? Well, we've known how to do that one for a very long time. It would just have its potential energy at the top and its translational energy at the bottom. Mass would cancel out. V equals the square root of 2GH. I know that sounds familiar to you. Pretty sure James carved that on top of one of the desks. So 2GH is going to be 2 times 9.8 times 5. That's 98. Square root of 98 meters squared per second squared. Square root of 98 is 9.89 meters per second. So if it didn't have to waste some of its energy spinning, it'd be going faster. Remember back to the sled versus the tire going downhill. At this point, you should be beginning to like formulate like a real understanding of all of this stuff, putting the things together, seeing the pieces line up and form a greater picture. I'm hoping that's the case, because if so, then this week's practice sheet, quiz, etc. should be no problem for you. Good luck. Adios, children.